All right, this video is just for the people that are wanting to retake the first test. So this is just not every single topic that was on the test, because this would be a really long video. This is just like the highlights of what I saw people doing wrong, and then of course the big calculations. Okay, there was a couple of multiple choice questions involving isotopes and figuring out number of neutrons and that were frequently missed. So isotopes are simply atoms of the same element that have a different mass. Okay, why do they have different mass? Well, if it's the same element, they've got the same number of protons. Okay, so all atoms of carbon have 6 protons, but their mass can vary because their neutrons vary. The mass is simply the total of the protons and neutrons. So in this case, with the carbon 11, we've got 6 protons, and then 11 minus 6, 5 neutrons. With this isotope of carbon, with the carbon 14, we've got 6 protons still, but there's 14 minus 6, 8 neutrons. All right. Yeah, I said all that. Okay, and then there was like 1 or 2 questions over groups and their names, and those were commonly missed. So there's 2 different ways of numbering the columns on the periodic table, the groups. There is the old-fashioned way, which I don't care for as much. The 1A, 2A, this is 1A, this is 2A. And then these are the B's and through here in the transition metals. And then it's 3A, 4A, 5A, 6A, 7A, and then 8A. I don't like that way. I just like to number it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 18 is the way I like to do it. But whatever, however you want to number it, the names are the same. So the first column, 1A, or just plain old group 1, is alkali metals. Group 2 is alkaline earth metals. These are the transition metals. And then 13 and 14 and 15, they don't have a name because you've got nonmetals at the top, metalloids in the middle, and metals at the bottom. They don't have a lot of similar properties, so they don't have like a name per se. Oxygens group 16, is called the chalcogens, and then group 17 is the halogens, and then the last column is the noble gases. All right, I also saw some issues with the multiple choice over formula writing and naming. First of all, if it's an ionic compound, you know it's ionic because there's a metal in it. So sodium chloride, NaCl, aluminum carbonate, Al2CO3, parentheses 3. Notice there's no mono, di, tri, tetra stuff in here, so don't insert prefixes into your ionic compounds. They're not needed. There's only one way that aluminum carbonate can exist. Aluminum's +3 always, carbonate's -2 always, and so you don't need it to say dialuminum. Anyone that knows how to write formulas could figure out that there's 2 aluminums. Now, the only exception there is with the some of the metals can have more than 1 charge. In that case, you use a Roman numeral. So like iron chloride would be iron 2 chloride or iron 3 chloride. You would include that in the name, indicating whatever the charge of the metal was. Now, in covalent compounds, because nonmetals can combine in different ratios, we do need prefixes. Like there's carbon dioxide, CO2, but then there's also carbon monoxide, CO, so we have to specify. Dinitrogen tetroxide. That there could be N2O3, N2O, NO, there's all different kinds of nitrogen oxide compounds, so we need prefixes in these. So do use the prefixes, but you don't ever put mono on the first element. Like we don't say monocarbon dioxide. We just, if the first element, there's only one of it, we just omit the mono. All right, acids. You know it's an acid because it starts with H. If it's just H and 1 nonmetal, you do the hydroic business. So hydro means there's no O. So hydrochloric, hydrobromic. Now, if there's a polyatomic ion in it that has O, well, then you just figure out the name of the ion. If it's an 8 ion, you change the ending from 8 to ic. If it's an 8 ion, you change the ending from I to us. So chloric, because this is chlorate, we call it chloric acid. You can't see it because of me in the corner. Can I try to move this? This is HClO3. Well, that's the chloride ion, so we call this chlorous acid. All right, and then I saw issues with calculations like this. If we know how many moles of a molecule we have, in order to figure out atoms of just an element in that molecule, we need to use a subscript. Okay, so we have moles of carbon dioxide, which using Avogadro's number, we can convert it to molecules of carbon dioxide. I can't call this atoms because this is not a single atom, it's a molecule. If I'm wanting to try to figure out atoms, I, in the next step, need to look at the subscript here. So I'm converting moles of CO2 to molecules of CO2, and to get to just atoms of just the oxygen, I'm going to say that for every one molecule of CO2, there's 2 atoms of oxygen. So basically, we're just converting to molecules and then doubling our answer because there's 2 O's. So don't forget that step. All right, here's another one that's a little lengthier. This time, instead of starting with moles, we have grams. So in 500 grams of water, how many molecules of water are present? Well, grams suck, so convert them to moles, always, and then use Avogadro's number to get to molecules of water. Ta-da, we're done. And remember, if it's molecules that you're solving for, you're usually going to get a pretty big answer. Now, there's a part B to this question. How many hydrogen atoms are in that water bottle? Okay, well, we're going to need that other step, that extra conversion factor at the end. So we go grams to moles, using the molar mass from the table, moles to molecules of water, using Avogadro's number, and then to get to atoms of just H, we multiply by 2, because there's 2 atoms in every molecule. Ta-da! And don't forget to write the times 10 part in your answer, too. Sometimes people, some calculators don't really make that real obvious, and so it'll be this big long number, and then a little space, and then the 25, the exponent there at the end. So that's why it's helpful to check and see if your answer makes sense. You know, if I left off this part, would it make sense to say there's 3.34 atoms of hydrogen in a whole bottle of water? No, it doesn't make any sense. All right, empirical versus molecular. We just need to know what those words mean. The empirical is simply the reduced formula. It's the lowest whole number ratio. The molecular may be the same thing, or it might be twice as big or 3 times as big. It's the actual true ratio. So some example true molecular formulas. We've got acetic acid here. Normally we write it as HC2H3O2. We keep one of these H's out in front because it's an acid, but I rearranged it for this example. And then we have formaldehyde, and then we have glucose. Well, these are their true formulas, but only formaldehyde is reduced also. So in the case of formaldehyde, the empirical and molecular formula would be the same thing. Now, if we reduce the acetic acid, we get this. Okay, so acetic acid reduces down to the same empirical formula. So does glucose. Okay, so acetic acid, formaldehyde, and blood sugar are obviously not all the same chemical. Their true formulas are different, but they reduce down to the same empirical formula. And when we do empirical calculations, that's what we come up with first, and then we can figure out the molecular. So we'll look at one of those. So let's say you're given percent comp and you're asked to figure out the empirical formula. Well, you take the percent, call it grams, then convert that mass to moles, and then divide by the smallest number of moles. The whole point of a chemical formula is it gives you the ratio of moles in that compound. So you have to convert the grams to moles and then divide by the smallest number to get the ratio. So here's an example of rubbing alcohol or isopropanol. Here's the percent comp. What's the empirical formula? Well, take the percent and just simply call it grams. Then convert the grams to moles. Now, don't do anything weird and try to make the oxygen diatomic and put 32 down here and O2 up here, because we're not talking about pure oxygen. We're talking about rubbing alcohol. And so it's not guaranteed to have 2 oxygens in it. That's you only make like hydrogen and oxygen diatomic if they're by themselves. All right, now once we have moles, we're going to divide all of the numbers by the smallest number. And I get 1, 8, and 3, which it worked out to be nice whole numbers for us this time. So C3H8O. So a little limerick to help you remember that. Percent to mass, mass to mole, divide by small, multiply till whole. Now that technique also works on those combustion analysis problems we're struggling with. They're just slightly different at the beginning, but after that, it's mass to mole, divide by small, multiply till whole. It's the same process still to get to the answer. So I'll have one of those in a minute. Now, how do you get the true formula from the empirical? Well, that's just one step, okay? The mass of the true molecular formula will be given to you in the problem. And once you figure out the empirical formula, here in this question it's given to us, it's P2O5. So what you have to do is use your reduced empirical formula to figure out the mass. It's coming back here. Okay, so we figure out the mass of the P2O5 of the empirical. Okay, 2 P's and 5 O's. Voila. Now it gives us the mass of the real one, 283. Well, 284 really. Just by looking, we can see that 284 is kind of twice the 142 here. So the real formula is twice the empirical. If you don't believe me, you can divide it and see. So the real molecular formula is just going to be twice as big as the baby empirical formula. So instead of P2O5, it is P4010. Ouch. And then you can kind of check your answer too. If you add up the mass of your molecular, your P4010, you'll get the mass given in the problem if you've done it right. All right, so here is the headache ones, where it tells us that combustion of a sample of this size produces this much CO2 and this much water. How do you figure out the empirical? Technically, if you wanted to spend more time on this problem, you could figure out the percent carbon in the CO2 and the percent hydrogen in the water. Call it grams, convert to moles, divide by smallest, multiply till whole. That'll take you a little bit longer, so I've just shortened it. If you just use this shortcut and go from grams of water to grams of hydrogen, just have to remember there's 2 hydrogens in water, so we need to use 2.02. That'll get you to grams of just your H. And then you can use this shortcut to get from grams of CO2 to grams of just carbon, and that'll get you grams of carbon. Do not overround in this step. I cannot emphasize that enough. Now, the third element is O. Well, how do we know how much O there is? Well, that's when the total sample mass comes into play. You simply could subtract the C's and H's, the grams of C and H, off of the grams of the whole sample, and the difference will give you the mass of your third element, okay, of the O. Well, now we have grams of everything. So, grams suck. You convert them to moles. There it is. Made sure not to round too much. And then we divided by the smallest number of moles. And there's our answer. Well, you can't see it right now, but it's C3H6O. All right, so all you are doing different in this one is just how you start it, just how you get to the grams of C's and H's and O's, or whatever your third element is. Once you get there, it's the same kind of problem that you did in Chem 1. You just take the grams, convert to moles, divide by the smallest number of moles, and there's your formula. You may have to double it or triple it if it doesn't come out to a whole number, but at that point you're pretty much finished. All right, we already did one like that. So just some reminders in that type of problem. Don't overround, you'll get weird numbers at the end. Keep at least 2 decimal places in your molar masses. If you end up with, instead of a whole number at the end, if you get a half, well, double all your numbers. If you get a third, triple all your numbers. And if you get a quarter, quadruple all your numbers. You can't just round it. Okay, I saw people rounding like 3.5 up to 4. That's not legal. Okay, you just have to double all the subscripts at that point. Now your third element could be nitrogen, oxygen, fluorine. It doesn't matter. Whatever it is, you're going to get the amount of it by subtracting off the total sample. All right, I cannot do this next one in 30 seconds, so I'll have to do another video.